experimental external flow boundary layer theory is very interesting and illuminating and gives us a general quantitative grasp of viscous flow behavior, but because of flow separation, the theory does not generally allow a quantitative computation of the complete flow field. In particular, there is at present no satisfactory theory except computational fluid dynamic results for the forces on an arbitrary body immersed in a stream flowing at an arbitrary Reynolds number. Therefore, experimentation is the key to treating external flow. Literally, thousands of papers in the literature report experimental data on a specific external viscous flows. This section gives a brief description of the following external flow problems. 1. Category is drag of 2 and 3-dimensional bodies. Drag of 2 and A. Blunt bodies. B. Streamlined shapes. Two. Performance and lifting bodies. Consists of three parts: A. Airfoils and aircrafts. Projectiles and finite bodies. And C. Birds and insects. For the further reading, see the goldmine of data compiled in various references, and in later chapter 9, we shall study data on supersonic airfoils, and at chapter 10, open channel friction, and chapter 11, turbomachinery performance discussion. In this chapter, we are first going to talk about drag on immersed bodies. Any body of any shape, when immersed in a fluid stream, will experience force and momentum from the flow. Force and if the body has arbitrary shape and orientation, The flow will exert forces and moments and all three coordinate axes as shown in this picture. It is customary to choose one axis parallel to the free stream and positive downstream. The force on the body along this axis is called drag. The force on the parallel axis to the free stream. The force on the parallel on the free stream and positive downstream. Is called drag force. And the moment about the axis, the rolling moment. Moment about the axis is called rolling moment. The drag is essentially a flow loss and must be overcome if the body is to move against the stream. Let me write the drag is a flow loss and must be overcome if the body is to move loss and must be overcome if the body is moved against the stream. A second and very important force is perpendicular to the drag and usually perform a useful job such as bearing the weight of the body. It's called the lift. Let me write the force. A very important force perpendicular to drag force and performs a useful job is called lift force. So we have also a definition here. The moment above the lift axis is called yaw. The moment about the lift axis is called The third component, neither a loss nor a gain, is the side force. And about this axis is the pitching moment. Side force which is a loose force or gain force, and it's called side force. And the moment about the lift axis is called the side axis is pitching moment. To deal with the three-dimensional force moment situation is more properly the role of the textbook on the aerodynamics shall limit the discussion here to lift and drag. So in this case we discuss lift and drag. When the body is symmetric, let me when the body is symmetry, has symmetry about the lift drag axis, and with airplanes, ships, and cars moving directly onto a stream, the side force, yaw, and roll vanishes. So, such as cars, ships, airplanes, for example, and any object has symmetry, the force, side force, yaw, and roll vanishes. Side force, yaw, and roll. And the problem reduced to a two-dimensional case. Two force, lift and drag. Lift and drag. And one moment pitch. A final simplification often occurs when the body has two planes of symmetry. For example, this picture. Let me provide the picture in next page. A final simplification often occurs when the body has two planes of symmetry, as this picture. vertical plane symmetry and horizontal plane symmetry were shown. The planes here, a wide variety of shapes such as cylinders, ring, and all bodies of revolution satisfy this. This requirement. If the free stream is parallel to the intersection of these two planes called the principal chord, so if the stream is parallel to the intersection of two symmetry planes, as shown also in this picture, called the principal chord line of the body, as also shown here. Principal chord of the body experiences drag only with no lift. In this case is parallel. We have the body only drag force, no lift. This type of degenerate one-force drag data in what is most commonly reported in the literature, but if the free stream is not parallel to the chord line, the body will have an unsymmetric orientation and all three forces and three momentum can arise in principle. In low-speed flow paths, geometrically similar bodies with identical orientation and relative roughness, the drag coefficient should be function of the body Reynolds number. In this type of problem, the Reynolds number is based upon the free stream velocity v and a characteristic length L. Usually the chord or body length parallel to the stream. The chord or body length parallel to the stream. For cylinder, sphere, and dots, the characteristic length is diameter. Sphere and chord its length is diameter. As we know, Reynolds relation is VL on the kinematic viscosity. Characteristic area. Drag coefficients are defined by using a characteristic area A, which may differ depending on the body shape. We have a relation for drag force, non-dimensional drag force on the rho V2, and characteristic area. The factor 1 second is our traditional tribute to Euler and Bernoulli. The area A is usually one of three types. Type 1, frontal area. The body as seen from the stream. Suitable for teak. Stubby bodies. Such as sphere, cylinder, car, truck. Such as sphere, cylinder, car, trucks. Missiles, projectiles, and torpedoes. The second form is the area plant form area. The body area as seen from above. Suitable for wide. Flat bodies such as wings and hydrofoils. Such as wings and hydrofoils. And 3, wetted area. Customary for surface ships and barges. These are three types of areas in the drag force application, especially in experimental works. The next video, this discussion will continue in the next video. Friction drag and pressure drag.